Okay, we're going to try and record on the Mac today. So mainly because I forgot my my Surface at home. Okay, all right. So welcome to our last meeting before spring break. Unless you all want to have class on Friday. Yeah. Now we get the words and the vocalizations from the class. Okay. My goal is honestly just to get the attendance updated and the exam graded, so that by the time you come back from break, everything's taken care of. Homework's good to go, though my TA's been doing a fantastic job there. I'm the one that's behind, not him. On the homework front, you do have a homework that I'm assigning today that is due Friday. It is an Excel-based homework, so you're going to be doing some plotting in Excel. That will become, fairly clear after today's lecture as to what it is you're going to do. And again, there's no class on Friday, so you're going to do the homework, turn it in on Friday, and then it's spring break land, which I know, at least for you folks who went through the ringer yesterday with your capstone presentations, you could use a break. Am I right? So, I'm sorry I missed the second half. So, I had conference calls, but first half everybody did very well. So, okay, everybody get the code? Okay, so how do I use a Mac again? Okay. Okay, all right, everybody. So we are going to be discussing a new unit in the class today, and that unit is the unit on columns. Actually, let me just do this and make it full screen like that. Okay, I'll say this about this unit in the class, and really columns and beams in general, is I think this is when steel design really starts to wake up and get fun. I really enjoy the columns and beams section in the class, probably more than everything else. Not to say I don't like bolts and welds or tension members, but this is really fun. There's a lot of really nifty stuff to chat about in this section. So the way that I do columns and beams is I usually take a sort of an aside and discuss the theory, because the theory is a little bit more involved with columns and beams than it is with tension members and bolts and welds. You can sort of integrate that, but we do need to take a little bit and discuss that. Okay, so I do want to mention right off the bat that we are going to be seeing some calculus in the next few slides and some differential equations. I'll say this, let me, because I've got my little animations here. I'll say this, I don't expect you to do the calculus. Okay? I want to be crystal clear on that. You do not have to do the calculus. You do not have to worry about that. But you are going to see some. Okay? What I'm going to do is derive for you the theory of elastic buckling, which, if you took Engineering 216, you should have done that near the end of the semester. So I'm hoping that some of you have at least seen this before, though it might have been some time. But what I'll say is this should be a refresher, but I'll take my time with it. Okay, so let's consider what I'll call a simply supported column. Okay, and by a simply supported column, I mean a column that is prevented at each end from translating, so it can't move left or right, but the ends are free to rotate. Okay. So both the top and the bottom can rotate, okay? And it is subjected to an axial load P, okay? Now, unlike a tension member, where the load is tending to elongate the member, the problem with compression members is that the loads not only tend to shorten the member, but tend to want to cause buckling, okay? And so I would say that the star of the show for the rest of the semester regarding columns and beams is this concept of stability, okay? The idea that as you're loading it in compression, or as there are components of a member that are in compression that we generate a sudden loss in stiffness and a sudden stability issue where the member will suddenly and almost freely deform, okay? So in the case of a column, we load it, we load it, we load it, we load it, and it buckles, okay? Now mathematically, we sort of treat that as sort of a bifurcation. It's either buckled or it's not. We'll talk a little bit later about how we need to refine those assumptions. Okay, so this is essentially a beam. Even though we're treating it as, even though we're loading it in compression, it is a flexural style element. So what we're going to do is we're going to break out our differential equation that we used last semester in structural analysis for beams. That the idea that you can relate the displacement in a flexural element to the moments by saying the second derivative of that displacement, or essentially the curvature, is equal to m over EI. So by the way, for this column, we're going to assume EI is constant, that it has a constant flexural stiffness. Okay, so I'm going to break out the samurai sword or lightsaber if I'm a sci-fi fan, and I'm going to cut a section, and I'm going to look inside the section right here, and I'm going to say, okay, what are the moments inside the section? Okay, well, if I cut a section through an arbitrary point in the column, I should assume that there is an internal moment present inside the column, but then that has to be counterbalanced by this moment that happens here. See, as the column buckles, there's a load here and a load here, so these loads are sort of forming a force couple. Remember that from statics, right? So if you have load that are parallel, acting in opposite directions, separated by a moment arm, that you get a moment from that, and that moment equals the magnitude of the load times the distance between them. Everybody remember that from statics? Okay, so what I'm saying is that the moment inside the beam is equal to Py, or really negative Py, because they're both acting in the same direction. At least I'm drawing this according to conventional sign conventions and whatnot. So if I substitute that into our differential equation, so I say the second derivative of deflection is m over EI, but instead of m, I throw a negative Py, I end up getting this differential equation, okay? So I'm getting that the second derivative plus some term times y equals 0, okay? So this is a second order differential equation, okay? And so we're going to treat it as a second order linear differential equation because we're going to treat essentially this term as a constant when we solve the diffie-cube, okay? I know for some of you, I'm bringing up Math 335, and you're thinking, like, I was having a good day, you know, so why are you doing this to me, Dr. Mike? Okay. Is this about right? Yes. Right? So what we're, I know things about stuff. All right, so what we're going to do is we're going to say y double prime plus, and then what we're going to do is instead of P over EI, we're going to do alpha squared times y, and I'll explain why here in a second, and I'll just use A. Okay, and so this is going to be our differential equation, and the reason why I'm using alpha squared is because when you look at the solution to the differential equation, you have an alpha term left over. So I'm basically just calling this alpha squared so that I don't have any square roots in my answer. Doesn't really matter. But that's one way of doing it. Another way of doing it is to just write the characteristic. Remember, r squared plus alpha squared equals 0. You get imaginary roots, all that jazz. So, okay. I can remember how to run a Mac. Okay. Okay, so again, what we're going to do, this is the differential equation we're going to solve. We're going to substitute this in right here. We're going to yield this differential equation, which is a little bit easier to solve. The second order linear differential equation, we have constant coefficients, and then we can solve that as follows. And again, you can solve that by saying, well, this is r squared, this is alpha squared, so r squared plus alpha squared equals 0. So r is plus or minus alpha times I, right? And remember, if you have plus or minus an I term, that's a cosine and a sine. Am I bringing this back from Math 335? Everybody remember this? Okay. So what I'm saying is that this term right here, this, okay, this is the solution to the differential equation for the buckled shape of the column. Now, to be blunt, we don't really care about this, okay? Because our goal is really to, like, we're structural engineers. We care more about the load that causes buckling more than we do the function that describes what the column looks like when it is buckled, okay? We're going to get there, but I just want to make sure everybody's got their eye on the prize. The goal is to figure out the load that induces buckling, okay? Is everybody with me on this? Now, but we're still in Math 335 land, so let's go to Math 335. How do we solve for C1 and C2? In general. You need, either initial conditions or boundary conditions, okay? And by the way, in engineering land, we tend to use the term initial conditions when we're talking about temporal conditions, so things like something at time equals 0, so like a position or a velocity, but we tend to use the term boundary conditions when we're talking about spatial situations, like the deflection here or the slope here. So that I'm gonna use the term boundary conditions, but if your Math 335 class used initial conditions, that's fine. So that's my little Wolfram Alpha joke that I got ahead of myself. Okay. All right, so we've got these two arbitrary boundary conditions, or these arbitrary constants that we need to deal with, and we're going to deal with those using boundary conditions. Okay, so keep in mind that this function, this y of x, what it's describing is what this shape looks like. So I've got the column sort of turned. So imagine this is the x-axis and this is the y-axis. So that y of x is describing what that shape looks like, which you can kind of tell it sort of looks kind of wavy, so it makes sense that we have cosines and sines. Everybody with me so far on that? Okay, so what are our boundary conditions? Well, what can you tell me about the lateral displacement here and here? 0, okay? So our two boundary conditions that we're going to utilize are that the function at 0, that should say 0. Whoopsie, I'm gonna fix that. That should say 0. That should say 0. Okay, so our first boundary condition is that the displacement at x equals 0 and 0, and the second is that the displacement at x equals L equals 0. So let's do a little bit of math and let's see what we get here. Okay, so let's solve for C1 and C2. Okay, so the first one, what I'm going to do is I'm going to plug in 0. Okay, so C1 times 0, C2 times 0. So let's look at this. What is the cosine of 0? 1. What's the sine of 0? So I have 0 equals C1 times 1 plus C2 times 0. So I get that. So that's pretty easy. Okay, so basically what I'm saying is that the first boundary condition makes all this hullabaloo go away. Fine. Okay, what about the second boundary condition? Okay, so the second boundary condition, what I'm going to do is I'm going to plug in L. Okay, I'm going to say C2 times the sine of alpha L, and I get this. So basically what this is saying is that in order to meet our boundary conditions, I've got this expression that has to equal 0. Okay, is everybody with me on that? Okay, this is actually kind of tricky. Okay, there's actually kind of a lot going on here. So I kind of want to diagnose this a little bit. Okay, let's talk about this. Okay, so I have here that this is now, so let's sort of recap where we are so far. This is this is our function for the displacement of the column. I have here that this has to be true, and let's remember that what is alpha? Well, we defined alpha as like alpha squared equals P over E alpha. Okay, so that's what we know so far. Okay, so what we're trying to do, like if we're in differential equation land, if we're in Math 335, we're trying to figure out what C2 is, and we have this going on. Okay, now I would argue this slide is sort of where Math 335 ends and CE 414 begins. Okay, so what do I mean by that? What are the mathematical ways that this expression can be true? Okay, give me like a way that this could be true. And let's ignore physics for a second.
The sign has to be 0.
What?
The sign has to be 0.
The sign has to be 0, but let's dig into that a little bit more. What I'm getting at is, could L be 0?
The left side would be 0.
Why are you saying no?
Because it's a length. It has to exist.
Okay, this is what I'm talking about. Okay, the mathematician says, well, L could be 0, right? But what we're saying is, no, L can't be 0, because that doesn't make any sense, right? Because for L to be 0, the column doesn't have any length. You see my point? This is where the math ends and sort of the engineering begins, okay? So could alpha be 0?
No, right?
Well, it could be mathematically, but not from an engineering perspective. What's the problem with alpha being 0?
It's
P over EI, right? And so if alpha equals 0, that means that there's no load on the column. Do you understand what I'm saying? So let's talk about this. What are the mathematical ways this could be true? Okay. Could C2 be 0? Well, C2 could be 0, but think about what we found. We found that C1 was 0, and we found that C2 is 0. So if C2 is 0, that would mean there's no displacement. And if there's no displacement, that means it hasn't buckled at all, right? That's not the point. We're trying to figure out what load causes buckling. And so if we're talking about a situation where C2 is 0, that doesn't make sense. I'm calling that a trivial solution, okay? Could alpha be 0? Or sorry, could L be 0? Yeah, L could be 0, but then that also doesn't make any sense from an engineering perspective because that's indicative of a column with no length. Same thing with alpha. Alpha could be 0, but then the column has no load, right? So what was it you said? You said something else. Could,
You gotta go to 180, right?
hold on, you're kind of onto something. You're onto something. But what I'm asking is, what about this being 0? Let's go to math land. When is the sine equal to 0? I'm saying this. Remember this? So isn't the sine equal to 0 at integer multiples of pi? The sine equals 0 at pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, right? Okay, so let's get into that a little bit. Okay, so I'm saying that if the sine equals 0, that is true if this term equals n pi where n is an integer, right? So I'm saying that we could write alpha as n pi over L. And then what we could do is we could say, all right, alpha squared is P over EI. Set those two equal to one another, solve, and we get this. Now, other than explaining what the deal with this n term is, like ignoring n for a second, would you agree then that we now have an expression for the load at which buckling occurs? The only issue that we've got to figure out is what is the deal with this term n, okay? Okay, so what's the deal with n? N is indicative of what's called a mode shape, okay? So the idea of a mode shape, so if we take the value of n and we start changing it, and notice how I'm only using positive values of n, because it doesn't really matter if I use negative values since I'm squaring it. Notice that as we use positive values of n, what we're seeing is a change in what the column looks like when it's buckled, okay? But the other thing that we're seeing is that as you change n, not only are you changing what the shape of the column looks like, but you're changing the load that causes that buckling, right? And I mean, do these mode shapes, are they really all that surprising? I mean, I don't know about you, but they kind of look like sines and cosines to me, and that was the solution of our diffie-q, right? So here's what I am saying. I am saying that if you have a column and you are loading that column, it's going to buckle when it's going to buckle, and typically what we're interested in is the buckling load that's the smallest, right? Which is the smallest buckling load? This, or this? It's that one, right? So if we kept increasing n, it wouldn't really matter. We would just get more intricate buckling modes, but higher loads that would cause those to happen. But that wouldn't happen in the real world. What would happen in the real world is this. So I propose that we now have a pretty basic expression for the buckling load. I propose that the buckling load, according to elastic buckling, which is what we've been looking at just now, is pi squared EI over L squared. Okay? Now, the other thing I'll tell you is that oftentimes what we're interested in doing is expressing this not in terms of buckling load, but in terms of buckling stress. Okay? Now, how do we calculate stress? Isn't it just sigma equals P over A? Right? Y'all remember that? So if I take this term and divide it by A, I would get a stress. Now, what happens is, if we do a little bit of algebra, we're left over with this term I over A, okay? And if you remember from mechanics, I over A, that's just the square, if you take the square root of I over A, you get the radius of gyration. Remember we talked about that earlier? So what I'm gonna do is replace this I over A with R squared, and so this is the buckling load, this is the buckling stress, and look what I got in here inside the term. What do I got here? L over R. Slenderness. Slenderness rears its ugly head again. Slenderness is going to become a very different animal in this unit of the class. Before, slenderness was just sort of something you checked, whereas now slenderness is going to become a very critical aspect of column capacity throughout this unit. Yes?
R is just a lookup, right? The radius of gyration?
Yes, for an I section or whatnot. For a W section, whatnot, yes, it's just a lookup. So, but again, you can also calculate it, just like this. So, if you were to take a W section, look up its IX, look up its gross area, and do this, you're going to get its R value. So. Everybody with me so far? Okay. Now here's the thing. Okay, well, I had a point I was going to make, but I'm actually going to hold off. I'm going to make that point a little bit later. Okay. All right. One of the things that we need to talk about right now is a slight adjustment to this solution, okay? So, and the way I'm going to adjust that solution is through what's called an effective length factor. And so I'm going to use the term K for an effective length factor. Why do we need to talk about that? Well, it's because of this, okay? The differential equation that we just solved was for this column, okay? Pin, okay? Well, what if I want to use that solution for this column? One that's fixed on the bottom and free on the top, okay? Well, the way that we handle that is we use what's called an effective length factor. And the way an effective length factor works is like this, okay? So if we look at a pinned column, would you agree that this is kind of what it looks like when it's buckled? Everybody agree with that? Okay. If I were to look at the buckled position or the buckled shape of a fixed free column, it's going to look like this, okay? Now, the way that effective length factor works is we say, okay, let's take that buckled shape and let's sort of extend it, okay? And if we notice, we've got this sort of distance between inflection points right here, because remember in math, like you've got this, and then it goes back, so that point's an inflection point where the curvature changes. Well, the same thing would happen over here, but that length between inflection points is twice the comparable length over here. Does everybody see that? So I propose that if we use this as the baseline, because this is what our solution is based off of. For a pin column, we'll take our K value to be 1, but for, say, a fixed free column, fixed on the bottom, free on the top, we'll take our K value to be 2, okay? And so basically what we do is instead of, pi squared E over KL, or it's pi squared E over L over R squared, it's pi squared E over KL over R squared, okay? And fortunately, effective length factors are simple lookups, okay? So if you go, this is way back in the commentary. This is on like 16.1-650. So if you open the manual, you're going to be in the pages of the manual that have the gray lining, like you're way back in there, okay? This is in the commentary. These are effective length factors for basic columns. So if you look at, for example, KC. KC is a pin column, so the K value is 1, okay? Now, one thing worth mentioning is that there are 2 rows here. There is a theoretical K value and a recommended K value. So the perfect one I like to use is this one over here. This is one that's fixed. See, here's the thing about a fixed column. Well, let's compare fixed versus pin. So the way a pinned boundary condition works mathematically is we assume that it is 100% free to rotate. So it has 0 rotational stiffness, okay? It can just rotate like crazy, okay? So again, a pin boundary condition is very much akin to the hinge on this door, right? If I apply a lateral moment, it's free to rotate around the hinge, okay? Whereas a fixed boundary condition allows no rotation at all. So another way of thinking about it is a fixed boundary condition has infinite rotational stiffness, right? It allows no rotation at all. But think about the numbers I'm talking about, 0 and infinite. is anything in the real world zero and infinite? No, right? If you do the math, you will find that for a fixed column, the theoretical K value is 0.5. But that assumes infinite rotational stiffness on the top and bottom. Nothing in this world provides infinite rotational stiffness. I don't care what it is, okay? So what we do is we say, here's the theoretical value, but we're going to bump that up a little bit, okay? So there's a difference between the theoretical K value and the recommended value for the purposes of design. So I want you all using this down here, not what's above, okay? Does that make sense? So again, we can derive a K value of 2 for a fixed free column, which is what we just looked at, but if we ever actually have that column, we're going to use 2.1 because this bottom is going to be a little bit looser than perfectly fixed. Does that make sense? Okay, so I'm just throwing that out there because we are going to see that a little bit later. Okay. Everybody with me so far? Now I'm going to hit you with the dose of reality. Okay, so I just prescribed to you a theoretical solution for column behavior. It doesn't work. It doesn't work. Now let me qualify that. I am not saying that the term for an elastic buckling stress is not useful. It is, okay? The solution that I just presented is useful in predicting column behavior. It's not enough though, okay? It's not enough, okay? There are two very big reasons why real column behavior deviates from ideal column behavior, okay? This will be a wonderful question on a celebration. The two big reasons are as follows. So the first reason I want to talk about are what are called residual stresses, okay? I'm not sure if this gets touched on in manufacturing land for you mechanical folks, but let's talk about the process by which steel rolled shapes are formed, okay? I posted that little how it's made video on the YouTube playlist. I'm not sure how many took a look at it, but essentially what you're doing when you have this, red hot steel is molten steel, is that you're producing a near net shape, right? And then you're feeding that shape through these pressurized rollers that take this really, chunky eye shape and sort of squish it down into the W14 by, what had 14 by 99 or the W10 by 49 that we're using for columns in buildings and bridges and flex homes, all that jazz. So you have this really hot section of steel that's gone through these pressurized rollers to generate a final shape, and then the section cools, okay? So you got this, hot steel that cools. The problem is that the steel does not cool at the same rate, okay? Specifically what happens is that the steel that's sort of on the outside, like the flange tips and like the center of the web, they cool first, okay? And then the section here, like where the flange and the web come together, they cool last, okay? So what happens is, remember how, when metal cools, it contracts, when it heats up, it expands? So because that's happening at different rates throughout the cross section, what's happening is that these flange tips are going into compression longitudinally, and then the flange web junction is going into tension in order to maintain equilibrium. To be clear, the column's not running away from you because of these what are called residual stresses. But I propose that if you were to just buy a section of W10 by 49 off the shelf right now, just buy a section, look at it right here, I guarantee you it has locked in stresses because of the differential cooling process. Now some of you might be going, well wait, Dr. Mike, doesn't that matter for tension members? Like why didn't you talk about this before? My response to that is tension members don't present a stability problem, okay? What's happening is as you load the section, so I propose over here on the left, this is what the section looks like before you put any load on it. As you put load on it, what's happening is that you're yielding the section at different rates. See, here's sort of what I'm getting at. So if we just assume a really, really basic stress strain curve, in other words, the section is linear up until Fy, and then it just freely deforms. This is sort of an ideal stress strain curve, assuming no residual stresses, but this is actually what's going on in a column, okay? And what I'm proposing is that as you increase that load, what's happening is more and more of the section is going to yield, and it's not going to yield all at once, it's going to yield gradually, and what that's ultimately going to do is drop the stiffness, and so it's going to buckle earlier because less of the section is effective in resisting that load. Does that make sense? See, in the land of tension members, because there's no stability, we just assume, like for gross section yielding, for example, we just blow through all this and we just sort of assume like that's our behavior. But in the land of stability, we do have to actually kind of consider that. I mean, we don't want a column wobbly because we didn't look at this, okay? So that's what's happening with residual stresses. The second reason why real behavior deviates from ideal behavior is the idea of geometric imperfections, okay? No column in this world is perfectly straight. No column in this world is perfectly plumb, okay? That does not exist, okay? This is the example I kind of like to use. So let's say that I am hiking in the woods, okay? And I'm hiking on top of a mountain. And Mr. Van Gundy doesn't like me very much, okay? Now, he decides I'm standing on top of the mountain, and he decides to shove me, okay? Because again, I said he didn't like me very much. I'm just messing with you. Now, what I'm getting at is if I'm standing right here like this and he shoves me, it's kind of easy to sort of, maybe it's somewhat easy to catch myself depending upon how hard he shoves me. But now imagine the same situation where instead of just me like this, it's me with an 80-pound backpack. It becomes a little bit more difficult, right? Because think about what happens, and think about this like from a statics perspective. So he shoves me, right? So I'm standing like this, I'm standing, plumb, okay? He shoves me, okay? So now the backpack is off my center of gravity, right? Which causes moment, which causes more deflection, which causes more moment, which causes more deflection, which causes more moment, which causes more deflection. So I sort of get that whoa, 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 whoa kind of effect, right? Does that make sense? That's called a second order effect, okay? And what I'm saying is when you go buy a column out from a service center and erect that column, it is not going to be perfectly straight up. It's going to have a little bit of this to it, okay? And it's also going to have a little bit of bow to it. It's not going to be perfectly straight either. Now I want to be clear, these tolerances are pretty reasonable. I mean, like H over 500 is sort of what you expect in a column erection in terms of plumbness. And I mean, just to give you an example, we're talking like 1/4 of an inch every 12 feet. Like that's not very much, but it's enough to affect what happens from a buckling perspective. See, like what happens from a buckling perspective, if you take a column, right, and you assume it is absolutely perfectly straight, what happens mathematically is you load, 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 and then you get here, sudden infinite lateral deflection. That's not how it works in the real world. In the real world, there's a little bit of an imperfection. So that buckling occurs gradually. But like by the time you're like here, for example, you already have quite a bit of lateral deflection. That column has deformed like crazy. Whereas you weren't accounting for that over here. Okay? So those geometric imperfections affect the capacity of the column a fair bit. So I propose the actual model that we're going to use, the model that's present in the AISC manual, accounts for residual stresses and geometric imperfections. And so what I'm focused on for today and for your homework that's due on Friday is the expression for Fn. And by Fn, so you know how we've been using a limiting stress of like Fy or Fu, right? So now what we need to figure out is what is our nominal stress that is allowable under a buckling situation for a column. Okay? And there's a little bit to it. Okay? So first off, we're now in chapter E. Okay? So if you go to chapter E, we're going to be looking at chapter E or section E2 and E3. Okay? So let me close this. Okay, so let me close this. All right, so let's take a look at this. So our phi value, first off, phi is 0.9, so there's that. Okay. One of the things that I include over here on the right, this is just to sort of help you navigate the spec. So anytime in the spec, at least for our purposes in the class, you see the term L sub C. L sub C is basically just KL, okay? The reason the manual uses the term LC, because I'm sure some of you are thinking, well, why didn't it just use KL? Why throw another term in there? Because there is an analogous term called L sub B for beams, okay? So the manual's trying to get you used to the notation, okay? And so the actual model for computing Fn is all of this. So the way that you would compute the capacity of a column is you would take phi times Fn times the area, okay? And what is Fn? It's all this, okay? So we can go through this if you want, but I find it a lot easier to just look at it as if it was a picture, okay? So basically the way that it works for a column capacity check is the first thing that you're going to do is figure out what the slenderness is, the L over R, or the KL over R, because you got to throw K in there, okay? And then basically what you're going to do is you're going to say, okay, here's my KL over R, and I have this expression here and this expression here. This expression over here, this one over here on the left, is what I'm calling inelastic buckling. And basically what I'm saying is that the column's behavior is governed more by the presence of those residual stresses. And what do those residual stresses do? They cause yielding to occur a little bit earlier than if you were to just assume perfectly linear behavior up to Fy. So that's why we say it's inelastic, because there's yielding occurring. So basically, so that's what this region's for. This region is elastic buckling governed by geometric imperfection. So basically what we're saying is we're taking the Fe value, this is what we derived, and we're backing it off a little bit. We're only using about 87% of it. Because what we're saying is that capacity right here, this is what we derived, but because the column's a little bit out of straight, because it's a little bit out of plumb, we back it off a little bit, okay? Now notice, but think about, does that make sense physically, okay? Well, this is L over R, okay? So describe for me physically, if this is L over R on this axis, what do the columns look like over here? With really, really low L over R values. Remember, L over R is a slenderness. So the columns over here are really, really short, stocky columns. They're not going to buckle, really, right? So this is Fy. And what I'm saying is if you have a really, really short column, the capacity is sort of like this, like really, really close to Fy. Whereas, what do the columns look like over here? Really long, thin, slender columns. So they're the ones that are going to buckle. So as your slenderness goes up, the capacity goes down, right? Doesn't that make sense, right? Because it's getting more and more slender, the capacity is going to get weaker, right? So the capacity is a function of L over R. Now, this term right here, this 4.71 square root of E over Fy, that's basically just if you set this equation and equal to one another and solve for this, that's what you get. So the manual's just doing that math for you, okay? So basically what you would do if you were to compute the capacity, figure out the L over R for the column, or the KL over R, figure out this term, and if your slenderness is smaller than this, you use this equation. If it's bigger than this, you use that equation. Does that make sense? So what I've done here on this slide is I've basically taken the equations that are in the manual and made them a little bit nicer. And so basically what I'm saying, so how do you compute Fn for a column? Like how do you do it? So the first thing that you have to do is you compute Fe. So Fe, that's just this, right? That's just what we compute out of mechanics, what we derive together. Our E value is 29,000 KSI, and then our KL over R is just the slenderness. Remember, be careful with units on slenderness because the lengths are in feet, but R values are typically in inches. And then you compute Fn. So if your KL over R is less than or equal to that, this is your expression. If your KL over R is bigger than that, that's your expression, okay? Now, this is really, really important, okay? So I really want this to make sense. Okay, I want to look at this equation right here, the one in the brackets. This is 0.658 raised to that fraction. This fraction Fy over Fe is an exponent, right? So if Fy over Fe was 0.4, it would be 0.658 raised to the 0.4. Okay, does that make sense? This is an exponent. It's not 0.658 times that fraction. It's 0.658 raised to that fraction. That is an exponent. Okay? Really important when you plot that. Anybody have any questions? All right, I do have one thing I want to show you just on Blackboard. And then I'm going to let you go. So if you go into the section on compression members, I made this little column curve animation. Y'all have probably used Desmos before, haven't you? So I used this little, I made this little column curve animation. So what I have here on the top is the Fy, okay? And so the way that it looks is the blue dashed curve, that's the elastic curve. That's what we derived, and I'm just cutting it off at Fy, okay? But the red curve, this is the AISC column curve. And so the cool thing you can do is you could change the Fy, and it will change what it looks like. So you can actually kind of see what it looks like. So I'm a dork. I thought this was really cool when I did this.
Very cool.
So, okay. With that being said, let me show you what your homework is. So your homework is, there we go. So I want you to produce a Microsoft Excel spreadsheet that will plot the AISC column curve, so essentially the red curve, for an Fy of 46 KSI. Okay, so you're going to put KL over R or LC over R, what have you, on the x-axis, and Fn goes on the y-axis. When you do your calculations, do from 0 to 200 in increments of 5, and make sure that your graph looks nice, you know, axis titles, all that jazz. I do give you some hints, right? So for simplicity, like what I would do in Excel is have one column here, and one column here. Whenever you're doing the math, at the very first row, at KL over R is 0, FE is technically infinite because you're taking pi squared E over this squared. But when you do the math, you find that Fn is just 46 KSI. So that very first row, you could just say Fy or Fn is 46. Don't use phi, like don't incorporate a phi value, that doesn't really matter. And I do think that if you use the if formula, it'll make your life a lot easier. So, and if you do it right, it should look like the red curve at the end of the lecture notes, or the red curve in Desmos. Sound good? Any questions? 7 minutes of your life back. Have a wonderful spring break, everybody.